Hello, welcome to yet another episode where we shall be looking at the proposed memorandum for the Physical Sciences paperwork for the June 2025 Limpopo Grade 12. So 153 hours, I'll push it and see. Okay, so how many questions you have? We have 9 questions that we're going to work with. Okay, and then leave a line between that. It's okay. It's the usual, okay? Question number 1, which is the multiple choice, they are telling us that the following diagram shows the presence of a perfectly horizontal force that is exerted on a box. Okay. Which one of the following equations can be used to calculate the normal force? So for us to get the normal force, we need the weight. Normal force must be equal to the weight, which weight is mg. So option A, I don't need to look at the other options. Then 1.2, according to Newton's second law, which of the following sketches best illustrate the relationship between acceleration and the mass? So we know that the mass and acceleration are inversely proportional, okay? So A represents a direct proportion, which is wrong. B, I don't know what he's talking about. Inverse operation is C, which is the correct option. D, that is something else. And then 1.3, in the equation, X is delta P over delta T. X probably represents, it should be the impulse. Is it impulse or net force? No, we know that impulse is just a change in momentum. And then the net force, because it is force, delta T is change in impulse. So it's the net force, which is A. Then the following velocity time graph, the following velocity time sketch graph represents the movement of an object. We saw this question in the May, June. Okay. That's not asking the same things. Okay. So which of, this is 1.4. Yeah, perfect. So which of the following statements correct describes the motion of the object? So the object dropped from a certain point or a certain height, and then it falls to the ground. Object thrown downwards and bounces twice to the ground. Object dropped and falls to the ground and bounces 3 times. Object thrown upwards falls to the ground and bounces twice. So the best option would be option D, because we're saying that it is thrown upwards. It falls to here it reaches the maximum, falls to the ground at this velocity, and then bounces twice. So this is going to be the first bounce. Okay, then it hits the ground again, and it's going to be the second bounce. And so we're going to have option D as the best answer there. Then 1.5, which letter P, Q, or ST indicates the highest point that the object reaches? So highest points will be Q, okay, and T. Highest points must be Q and T. Is that Q? No, because it can't be T, because this is velocity is 0. So probably this is when the object has stopped the bounce. Because at a maximum point, velocity needs to be 0. But 0 can also be an indication of when the object has stopped the bounce. So it's only going to be Q. Then 1.6, the kinetic energy of a moving object can be quadrupled, increased 4 times by kinetic energy of a moving object. So we know that kinetic energy, or sometimes we abbreviate it as EK, is given as a half mv squared. So if you increase it by 4 times, what happens to the mass? You double the mass, double the speed, half the mass, half the speed. What's going to happen there? 1.6, we're going to double the speed. Okay, because if you double the speed here, okay, then it's going to be like 2v squared, which becomes 4 automatically. Okay, so that is doubling the speed, option B. Then 1.7, The situation when rocks are sliding down a hill or mountain as shown on the road sign. Which of the following description will accurately describe the rolling or the sliding down of the rocks? And so what we notice here is that one, it is an isolated system and mechanical energy increases. It's an isolated system and mechanical energy increases. Or it's not an isolated, but mechanical energy increases. It's not isolated, mechanical energy decreases. Isolated, mechanical energy decreases. We need to decide, okay? Number one, the fact that we have external forces that are acting, okay, like wind, there could be vibrations and so on. Automatically, it's not an isolated system. So we're looking at option B and C, okay? Now, the fact that the height of the rocks will be decreasing, meaning that the mechanical energy must also decrease. So option C will be the best for that. 1.8, the magnitude of electric field at a specific point away from the charge can be determined using this formula, okay? Which of the following sketch graphs illustrates the correct mathematical relationship between electric field and the distance? So this E and the distance, they are inversely proportional, okay? Meaning that B would show the correct representation for inverse relationships, okay? So I'll go with a B. Then 1.9. Telling us that the following circuit diagram shows two identical resistors that are connected to a battery with internal resistance R. The switch is initially open, okay? Which of the following combinations below correctly represents the voltmeter and the ammeter? So when the switch is open, okay, the voltmeter reading will definitely decrease since no current, or because there's current that is flowing through this other R, okay? But when you open it, it simply decreases. Then the ammeter reading, since the voltage is small, where is the ammeter located? The ammeter is just on this side of the circuit, which means the ammeter won't be affected, should increase. What's the question saying? The switch is open initially. Which of the following represents when the switch is closed? Oh, so when we close it, okay? The fact that these two are in parallel, okay? The total resistance is going to be small, it's going to decrease. And when the total resistance decreases, more current is going to flow. And when more current flows, the voltmeter reading will have to decrease. Okay, because of the resistance in this battery, the cells. So we're going with option A. Okay, voltmeter reading will decrease and so on and so forth. Okay, why is the voltmeter reading decreasing? We've said that, no? Okay, then we move on to 1.10. They're telling us that the train driver is blowing a whistle as it moves through the station without stopping. The person waiting for the next train notices that the sound of the whistle is changing as the train approaches, passes, and moves away from the station. Which of the following combination will represent the frequencies that the observer hears correctly? Now, what we notice is that when you're approaching, the frequency of the listener is going to be greater, okay, compared to that of the source. So this is out, this is out, this is okay, this is okay. Then during the passing, the two frequencies need to be equal to each other, meaning that these two are still fine. And then when it moves away, the frequency of the listener must decrease. So meaning that option D would be the best. So 20 marks for that particular question. Then we move on to question number 2. A person loads a box into a truck. He or she, okay, we don't know, fastens the 48 kg box on a 4.3 kg trolley and then pulls it up a rough ramp inclined plane at a constant velocity. So constant velocity is 0 acceleration. Using a light inelastic rope, the angle of the ramp is 15, the angle of the tension is 28. Coefficient of kinetic friction is 0.22. Applied force is F that has a magnitude that is 3 times the frictional force. So F is 3 times the Fk, okay, the kinetic friction. We call it mu K. All right, there we go. Then the first question, they want us to state Newton's first law of motion in words. So we know that a body will remain, okay? We're saying a body will remain at rest, or we can say at a state, in a state of rest or uniform motion in a straight line, unless acted upon by an external force, or we can say acted upon by a net force. Unless it's acted upon by a resultant force, by a net force, or by an external force. So all those would be fine, but that is how that would be stated. So this is the same as inertia. Sometimes they can ask you to state the law of inertia. All right, 2.2, they want us to draw a free body diagram for the box trolley system as it moves up the ramp. So box trolley. Okay, the trolley and the box. So what we're gonna see is that there is a force applied here. Okay, and then we're gonna have the frictional force that is acting downwards. You can call it Fk. Then this is the normal force, definitely, which is the Fn. And then we're gonna have the gravitational force or the weight. So all I'll say, I'll have my F applied. I'll have my weight. And then I'll have my frictional force. It's going to be at an angle because these two are not, but it's not a big deal. Okay, Fk, and then we're going to have the Fn. Okay, so that is how I would have drawn that for 4 marks, okay? Then 2.3.1, they want me to calculate the kinetic frictional force between the trolley and the ramp. Okay, so I'm focusing on this top part alone. Okay, so what I'm going to do, number one, I can start by saying that my Fnet needs to be a 0. Where can I write it? Because they told us that the frictional force is 3 times. No, the applied force is 3 times the frictional force. So I can use that relation, okay? But I know that this applied force is also in 2 components. We're going to have the horizontal, which is going to be the F cos 28. And then we're going to have the vertical, which is the F sine of 28. That's also one thing that we can put into consideration. Okay, so what I'm going to do, okay, that I feel could be quicker is for me to look at what do they need? They want the kinetic friction. Let me use the kinetic friction formula and say that my Fk is equal to mu Kn, whereby I have my mu K and the N, which is the normal force, is given as the mg So like we said, we have 2 forces, okay? So we have this component of the F sine of 28, okay? And then we also have this one, the normal force. So we need to combine both of them. So what I'll say the mg cos of theta, which theta I'm focusing on is this theta. Is it 1 or 2? Someone's going to ask, is it 1 or 2? So with the frictional force, we normally use the angle of inclination of this. No? So that's going to be like theta 1. Then I'm going to subtract this component here, which is going to be the ft, the sine of, let's say, theta 2. Okay, substitute. They gave us the coefficient as 0.22 into, this is going to be a 48. Okay. But then we're looking at the total mass, which mass is going to be the 48 times, is it plus? Because they told us it's a 4.8. Is it a 4,8 or a 48? No, the trolley is 4,3, not 4,8. The box is the 48. Okay, so that's going to be 48 plus 4,3 multiplied by the 9,8 and the cos of 15 minus the 3fk. And then this is going to be the sine of 28. So this should be equivalent to fk. So let's open this up. When we punch this into the calculator, okay, we're going to move this that side. And then we add the fk, becomes a 4fk. Then you divide by the sine of 28, meaning that our frictional force is going to end up being 83,15 newtons. Okay, if you follow the calculations properly. So that is 2.3.1. Then they want the tension as the box trolley system moves up the ramp. Okay, so for us to get the tension, let's first get the force applied. That is going to make life a bit easier. So this is 2.3.2. So we know that the applied force is 3 times the frictional force. So 3 multiplied by the 83,15. Okay, that's going to be a 514, that's going to be a 9. And then this is going to be a 249,45, or someone could have a 46. So this is our force applied. So the force applied is more like the force that is within the tension, okay, because that is the same tension force that is being whatever. So that is how we would have gone about with this particular aspect. Then 2.3.3, they want us to get the normal force on the box trolley. Okay, normal force on the box trolley. Okay, now for us to get the normal force, yes, this question is something else. Ne? We know that our normal force, Fk, is given as the mu k multiplied by n, or from the frictional force, we have something like this, okay? And then for us to get the n, we have our 83,15, we're gonna keep it, okay? 83,15 is equivalent to the mu k, which we got as a 0,22 multiplied by the normal force. Okay, so if we do the division, meaning that our n is going to be 83,15 divided by the 0,22. The way I look at this question, it might have had quite a lot of answers to use. I mean, the range based on which approach you used. Okay, so this is 83,15 divided by 0,22. So this gives me a 377,95 newtons, okay? 377,95 newtons. Okay, so that is what I'm having. Then 2.4, define in words the term power as applied in physics. So we know that power is the rate at which work is done. Okay, rate of doing work, rate at which work is done. That is the simple definition that we can have, okay? Rate at which work is done, rate at which energy is expended or wasted. That could also be another aspect. So the person moves the trolley box system over a 5-meter long ramp in 3,2 seconds. Calculate the power that will be delivered. And so one thing we know about power, okay? We can start by looking at power being the work done over the change in time, okay? Now, our work done, we know that the work done is going to be given as the force delta x cos of theta over the delta t. Let me just combine everything at once. So the force that we calculated was 2 what? Let's go this side. It was 249,45. Okay, 249,45 multiplied by the displacement, which is the 5. And then we're multiplying it by the cos of 28. Okay, the cos of 28. And then what do we get here? Let's punch this into our calculator. No, but we said we're punching everything at once. So let's divide this by 3,21. Okay, let's just include it as we did that. So when I do that, the power that I'm getting is a 344,20 watts. Okay, so that is how we would have obtained our power. Okay, that the question simply wanted. Okay, so that is 2.5. Then question number, oh, what's going on? This is question 2, and then we have question 4. Oh, is everything okay? This is page 9. So question 3 is out. Let's hope it's hiding somewhere. Let's hope question 3 is hiding somewhere because we badly need it. Oops. Looks like it's in isolation. Let's see. Question number 4. A builder is standing on a crane A that is moving downwards at a constant velocity of 3 meters per second. He or she drops. Okay. I believe question 3 was supposed to be momentum, but it's not included in this question paper. I don't know why. He or she drops a brick B when the crane is 18 meters above the ground and then continues to move downwards at. Then after 1 second, he or she throws a second brick C and both bricks hit the ground at the same time. So if we take the upward direction to be positive, the following questions are based on the time, just as brick B is dropped until it hits the ground. The first question is, write down the initial velocity of B. A is moving at this constant speed. Then they drop B when the crane is this above the ground. So this velocity here, since it is constant, so it has to be also the velocity of B, which is 3 meters per second. Then they want us to calculate the time taken for block B to hit the ground. So one thing we know about block B is at 18 meters above the ground, that's when the block was dropped. So we have the displacement, which should be 18. Okay, then besides that, we could also, we have the initial, we have the displacement, and then we're just looking for the time. Okay, so let's see which equation of motion are we going to use? This is 4.2. 4.2. So if I use V final squared is equal to V initial squared plus 2A delta Y, is this gonna make sense? Because I need T, and if I use the displacement, I'm gonna have VI plus a half A delta T squared. I believe this could also be another approach, which I feel is the best, because now I don't have the final velocity and then I'm committing myself to finding it. Okay, so we know that our delta Y was 18 and the V initial was 3. Then we can just solve the quadratic. Okay, so it's going to be 18. Since they told us upwards to be positive, so the 18 is going to be negative, okay, since it's downwards. Then our V initial was a 3, okay, but that V was moving downwards also, so it's a negative delta T, and then plus a half multiplied by negative 9,8 with a T squared. Negatives could also be ignored and you just focus on the positive aspect of it, because if you divide through by a negative, you're going to end up with just a positive. So let me have 18 is equal to 3t plus 4,9 t squared. Okay, so when I have this, okay, this is plus 3t minus 18 is equal to 0. When I use the quadratic formula of negative b plus minus square root of b squared minus 4ac over 2a. So negative, this is going to be a 3 plus minus square root of 3 squared minus 4,9, negative 18 over 2 by 4,9. So when I punch this, I'll get two answers, but then the most correct answer of interest must be the positive one, which is 1,63 seconds. Okay, that is 4.2. Then 4.3, they want us to get the height from which the second brick was thrown. So how do we get this? So we're looking for delta y. Okay, because they told us the crane continues to move downwards. After 1 second, he or she throws one other brick C, and they both hit the ground at the same time. Okay, so what I'm going to do, I'll just find the displacement. Our initial velocity is still going to be 3. Okay, so it's going to be 3 multiplied by the 1 second plus a half times, it's going to be a half times 9,8 times t squared. Okay, but why must I even go that route? Because one, it's not going to make sense for me. One thing that I know, we have the delta t as 1 second, and then we have the velocity as 3 meters per second. So we know that the displacement should be, just divide the two. Distance over time. Eh? Yeah. What are you saying, Baba? What are you saying, Baba? For us to get the distance, speed is given as distance over time. So which means that the distance is going to be the velocity multiplied by the time. So our velocity is going to be 3 multiplied by 1, which is just 3 meters. Okay. But can we conclude that that is our answer? No, because this 3 is just the displacement with which the block just moved, okay, for that time. So the height of interest will be the 18 minus 3, which gives us the 16 meters. So this is an approach. But even with the delta y, if you say the initial and then that, I believe you could also get the same answer. Okay. Then 4.3.3, they want us to get the height of the crane at the moment that the two bricks decided to hit the ground. Okay, so what do we know? Or what do we have? Number one. Why am I saying 18 minus 3, 16? Yo, it's 15. Sorry about that. So that is 15 meters. They want the velocity with which the second brick leaves the crane before 4.3.3. Let's answer 4.3.2. So what I'm going to do, since I have my displacement, I'll have my V initial delta t plus a half g delta t squared. No? So this is negative 15. Initial is what we want, but after time of how many seconds? Do we have the time? Let's see. Initially, we had, there's a time we calculated for B, which was 1,63, meaning that the time for B is going to be 1,63 minus 1, which gives us a 0,63 seconds. So initial velocity VI multiplied by the 0,63 plus a half multiplied by the negative 9,8, and then 0,63 squared. Okay, so when I do my magic and change everything, I'm gonna end up with a VI to be a 20,72 meters per second downwards. So chances are high you're gonna get a negative answer, and then that negative simply represents the direction. So that is the velocity. Then the height of the crane. So what we're going to do there, we're just gonna get the displacement being V multiplied by T, speed, distance over time, and distance is speed times time. Okay, so the crane is moving at the same speed, which is 3, and then the time it takes is 1,63, because that's the time that it took for both bricks to hit the ground. Multiply that, you have 4,89 meters. What is the height of the crane at the moment the two bricks decided to hit the ground? So I'll get my 18, and then I'll subtract the 4,89. So this gives me a 13,11 meters. So that is what the question simply wanted. And then 4.4, they want us to draw a position time graph. So position time graph is usually curves of the movement of crane A, first block, second block, and blah, blah, blah. Take the ground as a 0 position. We must indicate the initial positions and all those aspects. Okay, so if I have this as my position, shall just say y in meters. This is the time in seconds, okay? So initially we had 18, because that was the height of interest. Then we calculated the 15 somewhere, and then we've also now calculated the 13,11 somewhere, okay? Did we calculate the 13,11? I remember seeing it somewhere. Yes, this one, the height of the crane. Okay, then what I need to do is that when you look at the time, if this is, let's say 1 second, this is gonna be 1,63. So it's saying both balls should be hitting the ground. So from here, there's a whole lot of mathematics involved here now. So let's just sketch this for now. We know that it's gonna be like that. And then the other one could be slightly with a smaller deflection, just up to that same point. And then we know that this is gonna be ball B, this is going to be the A1. Okay, then we can just bring about the 15, okay, just at 1 second. And then the 13,11 should be meeting up at that point. So the crane is just going to be at this particular point. I don't know how to draw a crane, guys. If that is our crane, so it's just going to be at that point. Okay, so that is that. Thanks to the drawings. Question number 5. A physics learner of mass 52 kgs skips over a rotating rope by jumping directly upwards. He or she, why don't they give people names? Manages to reach a vertical height of 47 centimeters above the ground. Neglect the effects of air resistance. Okay, explain what is meant by an isolated system. Okay, so we know that this is a system in which the external net force is basically 0. Then 5.2, can we draw a free label diagram of the learner when they are at the maximum height? How many marks is 1 mark? So this learner is just going to have the weight that is acting on them, okay, because there is no normal force since there's no contact with the ground and so on. Then 5.3, if we are to use only the energy principles, can we calculate the speed with which the learner leaves the ground? The only thing we know is that the vertical height is 47 centimeters, okay? And then the learner is 52 kilograms. So that's the only information that we have. Now, we need to go back to the conservation of, because they said we must only use the energy principles. So what we need to do is look at the conservation of energy to say that the mechanical energy at the bottom should be equal to the mechanical energy when the learner is at the topmost or the highest height. So mechanical energy is more like EP plus the EK. Must be the same. This is the bottom, this is EK plus the EP at the top. Okay, so you can combine the two, and then we try to look for that change in kinetic energy, okay, the EK, to get the network. So what we're going to have is that our EP at the bottom is going to be mgh plus a half mv squared, should be equal to the EK, which is a half mv squared plus the mgh. Now, one thing I know is that at the bottom, okay, the height is going to be 0. So this is most likely to go away. And then at the top, this is most likely to go away because the velocity will be 0 at the maximum what? At the maximum height. So what I'm going to have is basically a half multiplied by the 52 multiplied by the v squared should give me the mass, which is 52, multiplied by the 9,8, and then the height, because it was 47, change it to meters, which is a 0,47 meters. Then for me to get my velocity, I'll multiply, okay, this is going to be a 26. So v squared is going to be, but why don't I cancel these 52s and just multiply this by 2? So 19,6 times 0,47. Then find the square root on either sides, meaning that it's just going to be 3,04 meters per second. Okay, so that is the velocity that I'm having. That's the velocity that we are having. Okay, so that is to do with question 5.3. Then 5.4, when jumping, the learner must land and push himself or herself upwards to lift off the ground. Can we calculate the change in the momentum? Okay, until the moment he or she leaves the ground. So we know that change in momentum is given as the mass into, we can say, v final minus v initial, okay, because there's a change within the velocities. So the mass is 52. Our final velocity that we found was a 3,04. 3,04. We are subtracting 0. So this gives me 158, okay, comma, basically, let's say 0.8. This is kilogram meters per second. All right, then 5.5, can we write down the impulse of the ground on the learner during the motion as described in 5.4? So the impulse will be just the same, okay, but just in the opposite direction. So impulse is change in momentum. So 158,08, but then you need to indicate the direction also. This is upwards. All right. So 5.6, which is the last one for question number 5, they're telling us that after reaching the maximum height, this learner falls back down and reaches the ground. They must bend the legs while landing. Explain how this prevents the injuries. Refer to the net force, time, and the change while you explain. So this question would have also been brought about when you're talking about the purpose of the, what do you call those things in the cars? The airbags, yes. The effect of the airbags. So number one, we know that F net multiplied by delta T is giving us the change in momentum. Okay, explain how this prevents the injuries. So one thing we know is that F net is just going to be delta P over delta T. So bending the legs must increase the time. And when you increase the time, you'll be reducing the reaction force. So just tell us that the F net is inversely proportional to the delta T, and momentum remains constant. This is the beauty of physics, that you can even explain just using formulas and you get the full mass, okay? Alternatively, you can also tell us that as the time increases, the force will definitely decrease, while the momentum remains conserved or remains the same. All right, question number 6. We have a 35-kilogram child that wants to slide down a rusted 5-meter long slide. The top of the slide has a vertical height of 2.5 and the final height of 20 centimeters above the ground as shown. Okay, let's see the 20 centimeters. Oh, okay, for the final end. The child experiences a frictional force of 7.5 newtons. Can we define what a non-conservative force is? So a non-conservative force is basically a force for which the work done, okay, in moving an object between 2 points, will depend on the path that will be taken. Depends on the path that's taken. Then calculate the work done by the frictional force. So we can say that work done by the frictional force is going to be the frictional force, okay, multiplied by the displacement and then the cos of theta. That's the formula. We substitute, the frictional force was 7.5. The displacement, how many centimeters or meters are we moving? We are basically moving 5 meters because they told us a 5-meter long slide. Okay, so that is the distance to be moved. And then with friction, we always use 180 because it is opposite to the direction of motion. So this gives me negative 37.5 joules, or you can just tell us 37.5 in the opposite direction. Then 6.3, if we use the energy principles, we must calculate the speed with which the child reaches the end of the slide if the initial velocity is 0.3. So what I'm going to do, I'll say that WNC network should be equal to the change in EP plus the change in EK. Okay. Then alternatively, what I'll say is that the work done, okay, the network done should be equivalent to the mgh final minus the mgh initial plus, this is going to be a half mvm, I can say v final squared minus v initial squared, something like that, from that kind of aspect. Then we saw that our work done by the frictional force is going to be negative 37.5. Should give us the mass, which is a 35 times 9.8. The height in each initially. Let's factorize this and that, and then we subtract the heights. So initially the height was, what was it? Was it a 25 or is it 2.5? Supposed to be a 2.5. No? But then this is a 20. This is the final end. Okay, at a 20. So we're going to start with a 20, change to meters, which is 0.2. Okay, 0.2 minus a 2.5. Plus, this is a half times 35. V final is what we're looking for. The initial is 0.3 squared. Okay, so when you follow through and punch this in the calculator, I just did this once, which means my V final is a 6.56 meters per second. Now, remember they told you to use energy principles. Now, if you try to use the equations of motion, you're going to lose marks there. Okay, so it has to be just the energy principles, and then you answer that. That is question number 6. Question number 7, there's a racing car that makes a great amount of noise, okay, while moving at high speeds. A class wants to determine the effect of movement as observed frequency and ask the racing driver to assist in the investigation. They set up 2 detectors, okay, and let the car drivers let the car drive from detector A to detector B several times at different speeds. The car produces sound at this frequency, okay? And then one of the detectors records the frequency of this match. This is the frequency of the listener. Name and state in words the wave phenomenon that the class is investigating. So this is known as Doppler effect. Okay, so Doppler effect. And then how do we state Doppler effect? We know that this is the change, okay, in the frequency of sound detected by the listener because the sound source, saying because the sound source and the listener have different velocities relative to the medium of propagation. All right, then 7.2.1, they want us to name the independent. What won't be affected should be the speed of the car. And then what will be affected will be the observed frequency in this case, okay? Observed frequency, because the speed of the car is not going to affect, it's actually what is affecting. And then 7.3, which one of the detectors, A or B, recorded the frequency of 2030? They told us the car started moving from A up to B, okay? So meaning that B is the one that detected. Then suggest the reason for the answer that we gave. Okay, why are we saying it's B? Because they told us that the car produces a sound with the frequency of this, and then the detectors record. So the fact that the car produced 1.7, but the car is moving towards B, which means the frequency observed is going to increase. Okay, that should be pretty much the explanation. Or we can say that the detected frequency or the observed frequency is higher than the frequency of the car, than the frequency of the source or the frequency of the car. And then 7.5, they want us to calculate the speed with which the racing car is traveling. Okay, Doppler formula, we have V plus minus VL over V plus minus VS multiplied by FS. All right, then we just need to do the substitution. So this is gonna be 230 is equal to, they give us the speed of sound, or we must assume the 340. Okay, let's take the 340. 340. Okay, so that's a 340. Velocity of the listener is 0 over the 340. We're subtracting velocity of the source multiplied by the 1.7. So do your magic, cross multiply. So it's gonna be a 340 minus VS is equal to 340 times 1.7 divided by 2030. And then you do the subtraction, meaning that the VS is a 55,27 meters per second. Okay, so that is the velocity of the car. Question 8, we have 2 identical negatively charged atmospheres, A and B, placed in a glass test tube. They repel each other. A settles when the distance R between their centers is 25 millimeters, as shown in the diagram, okay? The mass of each is 20. Neglect the effects of air resistance. We're gonna do that nicely. Then can we state Coulomb's law in words? So Coulomb's law simply tells us that the magnitude, okay, of the electrostatic force is directly proportional, okay, directly proportional to the product of the charges, product of the magnitude of charges, and inversely proportional. Okay, inversely proportional to the square of the distance, square of the distance between the centers, between them. All right, between the centers or between them, there is no stress about that. Then 8.2, they want us to draw a free body diagram of sphere A. So sphere A is going to experience number one. We're going to have a force, which is like the Coulomb force upwards, and then it's going to experience the weight, the F of gravitational force downwards. So that's what sphere A is basically experiencing, since there's a repulsion already that's taking place. Then 8.3, they want us to calculate the magnitude on the charge of each. What did the question give us? They just gave us the mass, the displacement. What do we need? The magnitude of the charge. So the fact that these two are identical, okay? The fact that the two are identical. What I can do, I can look at Coulomb's law and say that it's K Q1 Q2 over R squared. We need this. We have that, we have that. We don't have the force. But from the free body diagram, we can get the force actually. Oh, hallelujah. So you can say that the force is equal to the weight, meaning that the force is going to be 20 multiplied by 9,8. We need to change the 20 to kilograms, which means times 10 to the negative 3. Okay. So what does this give us? Should I just continue? No, let me just leave it as this, okay? I'll simplify it later on because that's going to be 196 now. Times 10 to the negative 3, which is 1,96 times 10 to the negative, something like that. But it's fine. Let me just leave it the way it is. Then from this formula, I can now do the substitution and say that the 20 times 9,8 times 10 to the negative 3 is equal to K, which is 9 times 10 to the 9, multiplied by the Q squared, since they are identical, over the distance between them, which is 25 millimeters, okay? I need to change the 25 to meters, which is a 25 over 1,000. I square that. Okay, so meaning that my Q is going to be the square root of 20 times 9,8 times 10 to the negative 3 times the 25 over 1,000. This is squared. And then we are dividing it by 9 times 10 to the 9. Okay, so when I do that, my Q simply becomes 1,17 times 10 to the negative 7 coulombs, or 11,7 microcoulombs. Then 8.4, can we draw electric field pattern due to sphere A and B? Now, since the charges are the same, and we're seeing them as being positive or negative, which one is which? They told us two identical negatively charged. Okay, so they're going to repel each other. That's 8.4. So we can have this as our A, then this is our B. And then we're going to have something like that. Let's have that. Now, since they remember the number of field lines that are leaving one end should be just the same. So 1, 2, 3, 4, 5, 6. This is 5. And then we can have that. So they must just be coming in. So something like that. So basically, that's all we need with the field lines. We just need to see a region of 0 force in the middle there. Then 8.5, can we draw calculate the electric field of B at the center of sphere A? The electric field of B at the center of A. Now we know that electric field is given as KQ over r squared. So that's a 9 times 10 to the 9. We are multiplying it by the charge, 1,17 times 10 to the negative 7. We're dividing it by the distance apart, which is 25 times 10 to the negative 3. This will be squared. So just punch this into the calculator. I'm going to end up with 1,68 times 10 to the 6. This is Newton per coulomb. That's basically what the question wanted. All right, so that is question 8. Then question number 9, which is electricity. It's the last question. Hallelujah. Okay, so the battery with an internal resistance of 0.7 ohms is connected in the circuit below. The switches are both open, as we can see. R1 has a resistance that is twice R2. Okay. R1 is twice R2. Then they are telling us that when S1 is closed, okay, we close this, the reading of the voltmeter V1 decreases by 1,7 V. And the reading on V2 becomes 5 V. Okay, because when it's closed, current is just passing through this 2 ohm, R2, sorry. The 9.1, they want us to state Ohm's law. So Ohm's law simply tells us that the potential difference across a conductor, is directly proportional to the current, at a constant temperature. They want us to get the current in R2. So we have the voltage here, which is 5V. Do we know the resistance of R2? Do we know the resistance of R2? Nope. Nope. But let's see. If we cannot get it from here since we don't know the value of R2, but we can come and look at this internal resistance here. We can look at the internal circuit, okay? Knowing that V internal is given as IR. So when that switch is open, we're gonna have a 1,7 is equivalent to 1 multiplied by 0,7. 1 multiplied by 0,7, which is the internal resistance. What is the question asking for? We're looking for the current. So our I is going to be 1,7 divided by the 0,7, which gives us a 2,43 amps. Okay, then they want us to get the resistance R1. So for us to get R1, let's start by R2 here. So we know that if RV is equal to IR, the voltage is 5. The current is 2,43 R2, meaning that our R2 is going to be 5 divided by 2,43, first of all. Okay, meaning that our R2 is going to be 2,06 ohms. But we know that R1 is 2 times of R2. So I'll say 2 multiplied by 2,06, which gives me 4,12. Is it correct? Something like that. That's what I'm seeing. 4,12 ohms, okay? That's what I'm seeing by my calculator. The 9.2.3, they want the EMF for the battery. So substitute into the formula of the EMF. Still the switch is, one switch is open. We know that I into R plus small r. But is this gonna help us? Is this gonna help us? It should. So we know that the total current is just gonna be the 2,43, okay? Because we're just looking at a one-way, okay? We're just focusing on this one resistor. This one is out. Okay, so it's gonna be 2,43 into the R that we calculated, which is a 2,06 plus Okay, we're seeing this R2 and now we're also seeing the R1. So 2,06 and then the 4,12. 4,12. The internal resistance is 0,7. So our EMF is ending up at 16,72 volts. All right, so that is the EMF. Now they're telling us that S2 is now closed and then the results in a change in the value of V1. They want us to get the reading of A. So now what we're going to do there for 9.3.1. If we close this up, okay, remember our R2 is 2,06. So these are in parallel. So for us to get the effective resistance, we can talk of the product over the sum. I prefer using that approach. Yeah? So say the product over the sum. This is for the parallel one. So our product is going to be 2,06 multiplied by 15 over the 15 plus 2,06. When you punch this into the calculator, you're going to end up with 1,811 ohms. Then this we must plus the R1 because now this component and this will be in series. So 1,811 plus the 4,12, which becomes 5,93 ohms. Okay, so this is our effective resistance. What is the question asking for? The question is asking for the reading of the ammeter. Now, since we have the effective resistance, we can now go back to the EMF formula and look for the I. So EMF is given as I into R plus small r, okay? So meaning that our I is, we have the EMF as 16 because we calculated it initially as 16,72. We're dividing it by the big R, which is 5,93, plus the 0,7, the internal resistance. This gives us 2,52 amps. All right, so that is how we would have answered 9.3.1. The 9.3.2, they want us to get the power that is dissipated in R2. The power that is dissipated in R2, there are two ways to this. Number one, we can say that power, remember we're looking at R2, okay, in R2. So we know do we know the current that is passing through R2? No, we need to calculate it first, okay, because this switch 2 is now closed. So what we're going to do, we can get the voltage across R1, okay? V1 is gonna be, do we know the current? Yes, we just got the total current now as the 2,52. So V is equal to IR, meaning that 2,52 multiplied by the R, which is 4,12, we're gonna get our voltage there, okay? That's what I'm having now. But this is gonna make sense. It should make sense. It should make sense. Because if I look at the total effective resistance here to get the total current passing through this, that's gonna be a bit weird, but it could be an option that I can use. Okay, let me just omit this for now. Let me just use that other one for the par component. Okay, so if I get the 2,52 multiplied by 1,811, this is gonna give me 4,56. Then for me to get the power, I know that power will be given as V squared over R. So 4, is saying it's 4,56 squared because that's what we got. Okay, I'm gonna divide it by the resistance of R, which is 2,06. So this must give me 10,09 watts. All right, guys, so that's how I would have gone about it. But alternatively, you could also look at the fraction current, or you could use the approach that I was taking in the first place, whereby you get the voltage of R1, then you subtract from the total voltage so that we have the voltage of this, okay? And then we go on and do the other calculations. Okay, guys, so I'll stop there. There's no question 3, so we have to end at that. I wish you guys all the best in your preparation for paper 2. For those that have not yet written paper 1, all the best. Let's meet then. Bye-bye.